Okay, so let's look at problem 2.27. Here we are looking at an electron in a rectangular well with a well depth of 20 eV, and the lowest energy level is 3 eV, and we need to find the width of the well. So here, in order to find the width of the well, we need to make use of two equations, 2.34 and 2.35, which are given on page 29. So 2.34 talks about two constants, dimensionless constants. One is epsilon, which is the ratio of the energy level and the well depth. And then you have P, which is a function of the potential and the length. So in order to find the width, in order to find the width of the well, we need to find out what B is, right? Now, if you were to take a look at equation 2.35, that actually gives the relation between epsilon and B. And that relation is this. So from this, so first we're going to find the value of E. We're going to plug it in here and solve this equation. Then we're going to find the value of B, which we're going to plug back into this equation and then find the value of L. So let's take it one step at a time. Let's compute epsilon first. Epsilon will be 3 eV divided by 20 eV. The units get cancelled if this is a dimensionless constant, so that makes perfect sense. This will be 0.15. The value of epsilon is 0.15, right? Now let's plug this value in here. So 2 times epsilon is going to be 0.3. This one. Sine of, let this stay this way. We'll plug those values in later. So I can bring this to the other side of the equation, right? So if I can write it as equal to 0.15 minus epsilon square will be 0.0225 or half, and cos b. Okay. So if I were to divide everything by cos, the cosine term, just write that on better way. Now I can just, cancel this. This is going to be equal to 1. So we ignore that. And I can write this as negative 0.7 times tan of this is equal to whatever this value is. So let me compute this value. 0.15 minus 0.0225. We're going to take a square root of that, multiply it by 2. That'll give us 0.71414. So tan of this is going to be negative divided by 1.0202. Right, so what we need to do now is take the inverse. All I'm going to do is just use the Omni calculator on the internet and negative 1.020 02, and that gives me the value of negative 0.7954 plus n pi. So the reason I have n pi is because if x is the same as tangent of x plus pi. So tangent keeps repeating itself after every pi radians. So when we take the arctan, we take the inverse, we're going to add n pi, right? So where n can go from 0, 1, 2, so on. Now let's think about it. If n is equal to 0, then what happens? It's equal to minus 0.7954 because 0 into pi is just 0, right? So, and we know that this is a positive quantity, this is a negative quantity, and we know from the previous problem that b has to be greater than 0. We know from the definition of b that it is positive, it cannot be equal to or less than 0, right? So having n equals 0 results in a contradiction. It doesn't give a meaningful solution. So n cannot be 0 here. Now let's try n equals 1. That gives you negative 0.7954 plus this is pi divided by what is the value of square root of epsilon. Epsilon is 0.15, so the square root of that is 0.3879 something. We don't need so many digits in the so b is going to be 6.05 is what I get for the value of b. Okay, so now that we have b, let's try to compute L. Oh, before getting into that, now what happens if n is greater than 1? What if we go for n equals 2 pi or 3 pi or 4 pi? So as the value of n increases, the resulting value of b is also going to increase, right? Because it's directly proportional. You're adding a big number, b is going to be higher. Now, let's see how that impacts the width of the well. So b is this, right? So the width of the box is going to be ph over 2 pi, like this, right? Now, if the value of b keeps on increasing, the computed L, the computed width of the rectangular well is also going to be higher. As the width of the well is going to be higher, it means that you're going to have more and more energy levels. You're going to have more and more bound levels. And in such wider wells where you have so many bound levels, 3 electron volt level is not going to be the lowest energy level. The question clearly states that 3 eV is the lowest energy level. So it's safe to stick to the value of n equals 1 because that makes the most sense in this case. And let's just plug in the values and compute the value of L. So L is going to be 6.05, 6.626 into 10 to the power 34 joule second divided by 2 pi. We have mass of the electron, right? 31 kgs at 20 electron volts, right? 31.6 into 10 to the power minus 19 joule per eV. Well, let's actually take a look at the units, right? The numerator, you have joules. Right? Joule is Newton per second. Newton is kg meter per second square. And this results in kg meter square per second. Right? Now let's take a look at this. We have kg, a kilogram times joule. Divide the kilograms times Newton meter, meter per second squared times meter. So it's going to be basically kilogram squared, meter squared per second squared. So this is under root. So under root is just going to be kg meter per second, right? So now let's actually do the computation. And to solve for this, as we have shown previously, the units are going to be kg meter squared per second divided by kg meter per second. So you see this gets cancelled, this gets cancelled, we end up with just meters, which is what it should be. And now let's actually compute these values. This is what we get. Now, if we further simplify, um, 10 to the power minus 9 meter. So the width of the box is 0.265 nanometers.